Hello everyone, in today's lecture we will discuss that what do we do with the symmetries of partial differential equations. Now students, from the ordinary differential equation that is written in terms of two variables x and y and invariant under the transformation given by equation number 3.17, means x bar is equals to x plus epsilon capital X of xy plus order of epsilon square, and y bar is equals to y plus epsilon capital Y of xy plus order of epsilon square. And we found a change of variables by solving the system of equations given by 3.18, like capital X Rx plus capital Y Ry is equals to 0, and capital Sx Sx plus capital Y Sy is equals to 1. And with the introduction of these new variables r and s, the original equation is transformed to one that is independent of s. And from our previous chapters, you know that we have also solved particular examples, and when we use the change of variables technique, then at the end we are given with the equation that is independent of s and it is in terms of one variable r. So to illustrate this fact further, consider the infinitesimal operator gamma that is associated with this equation. Okay. We know that our OD is in terms of two variables x and y, so our infinitesimal operator is also in terms of two variables. So if we consider another variable, so we also need to write another term, like if there is a variable u, so we will also write over here plus u partial by partial u, but that is in the case of PDs, like in our previous lecture if you remember. So we have defined our gamma in an extended form. Okay, so gamma is written in equation number 3.19, and we want to apply the change of variables technique, means we want to convert x, y to variables r and s, or r is a function of x and y and s is also a function of x and y. So we want to apply change of variables, so we will write partial by partial x and partial by partial y by using the chain rule in terms of r and s. Means we can write capital X as it is, and partial by partial x can be written as partial by partial r by partial x, and also in terms of s like partial by partial s and partial s by partial x, plus capital Y as it is, and we also implement chain rule here, so we will get partial by partial r into partial r by partial y plus partial by partial s by partial y. So you know that we can write partial r by partial x as rx and partial s by partial x as sx and rest of the terms as it is, and similarly we can write it for the value of y. So students, if we collect the terms of partial by partial r and take it as common, and also the partial by partial x and take it as common and write the rest of the terms in the bracket, so we will get this one, like x rx plus y ry into partial by partial r plus s sx plus s plus y sy into partial by partial s. Now students, if we use equation number 3.18, now you can easily see that the term that is inside the bracket is actually this one, that is equal to 0, and the other one is equals to 1. So if we apply this equation, this condition, we will get 0 into partial by partial r plus 1 into partial by partial x, and that is actually equal to gamma, or we can simplify it like gamma is equals to partial by partial s, which represents that the new ordinary differential equation admits translation in the variable s, that is new ODE is independent of s. Okay. Now students, as I'm discussing earlier, we now attempt to extend these ideas to partial differential equations, like consider the infinitesimal operator associated with the infinitesimal transformation, and you know that in PDs we have three variables like t, x and u, and gamma is written as this one. And if we introduce new independent variables, you know, in the ODE's case we have defined new variables r and s, but here we have defined new dependent variable new, so we will write it as r as a function of txu, s also as a function of txu, and new as a function of tx and u. And then under the change of variables like these ones, the operator will become, so we can write gamma as this one, and similar to the case of the ODEs, we will apply the chain rule and collect the terms, so we will get this one, like first of all we will write it as t, and apply chain rule on this one, and then on chain rule this one, so we will get this term and u as it is, and we will apply chain rule on partial by partial u and we will get this term. And if we collect the terms of partial by partial r, partial by partial s, and partial by partial nu, so we will get these ones. And if we choose, like we will choose t r t plus x r x plus u r u is equals to 0, t s t plus x s x plus u s u is equals to 1, and t nu t plus x nu x plus u nu u is equals to 0. And if we choose these equations, so we are left with equation number this one, like if we substitute equation number 3.22 in equation number 3.21, we will get gamma is equals to d by ds. Okay, so what this means? This says that after the change of variables, the transformed equation will be independent of s. So what does this mean? If the original equation has the form this one, then the transformed equation will be of the form this one, because you know that we have implemented the change of variables technique. And if this equation is independent of s, then definitely our new equation will be in terms of r and nu. So students, the transformed equation is still a partial differential equation. However, if we assume that we are only interested in solutions of the form like nu is equals to nu of r, then equation number 3.23 can be written as this one, that is an ODE. Now students, in the coming lecture, we will implement this all procedure on example number 3.2, and we will see that the resulting equation, like when we solve heat equation, then at the end we are left with the equation that is in terms of variables nu and r, and that is an ordinary differential equation and easily solvable equation. Okay, so this is the benefit of using symmetry analysis of differential equations. Using symmetries and using transformations means we can convert a difficult equation that is in like a partial differential equation is converted into ordinary differential equation. And you know, we know a lot of methods to solve the ordinary differential equation, and our task is easy here. Okay, so this is all about this lecture. I hope you understand it. Thank you so much.